Okay, we can get started. Any questions from the previous class? Anybody has any doubts, questions? Please speak up, unmute yourself and ask. We can start from Tirundapuram. Priyadarshani, Gauri, Onkar, Deeptanu, any questions? Thanks.
No questions.
No questions? Okay. Any questions from Puneet?
No, sir.
Any questions from Bhopal? Doubts, clarification? Yes, Pooja.
Operator, or it's a square of I only.
It's a square of I only.
Then on taking the square root of I square, we are getting different this.
So you're asking why is I square equal to I into I plus 1? Is that your question? Then?
The I operator is equal to M H cross.
IZ is MH cross.
Okay.
I square is H cross square I into I plus 1. Do you understand? Okay.
Every X and I or Y, there will be different.
That's correct. Right? Okay. Just to solve her question, how will we get IX and IY? Since you said IZ on a given state, YLM is MH cross YLM, right? So the question, let me write it down so that this doubt, if it exists with others, can also be clarified. Okay. Well, let's formally welcome. Good afternoon, everyone. Let's start today's class. There was a question that was asked. So as to clarify, I'm writing things again, which will help you understand this better. I'm sure this you may have learned in your quantum mechanics course. I'm just writing it again. Basically, the spherical harmonics are eigenfunctions of the LZ operator, and they're also eigenfunction of the total angular momentum operator. It's just borrowing whatever we learned from there. And the question that's being asked here is that how do you get the certain set of eigenvalues? That depends on the properties. Since you're taking the Z projection, you're going to get the M quantum number out of it. If you're trying to get the total angular momentum, you pick the L quantum number out of it. This is what you would have learned in your quantum mechanics. Basically, for people who are still unclear what's happening, who may not have basics from quantum mechanics, generally you have an eigenvalue equation, which is if you operate a certain function with a specific operator, if the function is an eigenfunction, you get a constant and the same function back. What do we mean by this? When you operate something in a given function, if the function is an eigenfunction, you get a constant followed by the same function back. So if you're wondering what is it, you can think of something like d by dx on e power ax gives you a times e power ax, where you see this is the function, you got the same function back, where a is a constant. Okay. And whatever we are writing with the ket notation here, these are also functions. In quantum mechanics shorthand form, we tend to write a ket in this fashion. And therefore, you operate the Z operator of the angular momentum, the Z projection of the angular momentum operator on YLM. You pick out the M quantum number. Of course, H cross is a unit of, it takes care of the units and dimensions. And similarly, you operate L square on YLM. You're going to pick L as H cross square, L into L plus 1. Okay. We are just replacing L into I, and therefore, anywhere you have this, you have the same principles that work out, and therefore, we are borrowing the solutions from there. Does that make sense? Is that clear now? Where the modulus of L square, or rather the square root of L square, gives you the length of the vector, which is why we had H cross times square root of I into I plus 1. And therefore, what you end up getting is length of the vector for spin half system is root 3 by 2, while the projection is half. And therefore, we determine what is the angle. Major reason why we did this is to highlight the fact that the quantum magnet behaves differently from a classical magnet. So let's reiterate what all we learned. In the first class we learned you need to have an element with a non-zero nuclear spin so as to make sure it's NMR active. And we reduced ourselves to spin half system in this course because that gives you only two eigenfunctions. Therefore, it's very easy for us to understand these two states are there. How are the populations going to interact? The next thing that we looked at is, okay, if that's how it is, what is the total energy for the system? And we learned the total energy for the system is going to be given by the Hamiltonian, which is going to be minus mu dot B, where we said the external static magnetic field is going to be along the z-axis. The mu is proportional to gamma I, where I is the total spin, nuclear spin operator. And of course, it has its own components along the XYZ coordinates. Since the B naught is only applied along one of the axes, the other parts are not present anymore. Therefore, only the IZ component comes. Therefore, the Hamiltonian reduces itself to something very convenient for us, minus gamma B naught IZ. And therefore, we were trying to ask what is going to be the Hamiltonian in the alpha state and the Hamiltonian on the beta state. And then we were able to appreciate the fact that when gamma, the gyro-magnetic ratio is greater than 0, the alpha eigenstate is the lower energy state with the energy gamma h cross B naught by 2, and the higher energy state is gamma h cross B naught by 2. And therefore, the energy difference that we were talking about between these two states is going to be given by gamma h cross B naught. And I also asked you guys to figure out for a given B naught and a given spin. Therefore, you can figure out what is the energy difference between the states, which is commonly represented in the unit of hertz. And therefore, we were able to see that for something like 11.47 Tesla, the energy difference corresponded to something like 500 megahertz. And for a similar example, we also tried to look at what will be the population distribution. And we learned that when you're taking spin system, the population difference between the beta and the alpha state is rather small. It's more or less similar to each other. If I remember right, this was like 0.9992 or 492, I forget now. There's a small population excess that comes up in the alpha state or the beta state. And immediately after that, what we were trying to understand is that what are the overall orientation of these nuclear spins for a spin half system. We realized that the alpha state is going to be parallel to B naught. Once again, let me remind you guys, this is for gamma greater than 0. If gamma was less than 0, the state that's going to be more aligned with B naught will be the beta state. Remember, the energy levels flip, and therefore the same thing will happen here as well. So then we said it's either in the alpha or the beta state for a single isolated spin half system. Then we went to an example of what happens to an ensemble of spin states, which is where we were able to see, based on their population difference, the number of alpha and beta spins will be oriented at the magic angle, but their x and y projections, or rather the transverse plane projections, will mutually cancel out each other, and which is what we call as the random phase approximation. So what this says is that there will be no magnetization in the transverse plane, but interestingly, the longitudinal projection for the alpha and the longitudinal projection for the beta will sum up, which will once again destructively interfere given that they are opposite to each other, resulting in a small magnetic excess along the static magnetic field for your sample. And I kind of concluded the previous class by trying to say all information, that content that you need is present inside it. So therefore, let's try to see how we will measure it. So today's class will be going further in detail into this. One of the aspects that I would like to go further in detail is in understanding how still a single spin half system will be as a function of time. What do we mean by this? Let's just take a system prepared in the alpha state. We are talking about an isolated spin half system. And now the question that comes up is that if you're taking this isolated spin half system, how will it be in a static magnetic field B naught? Is it going to be remaining static there, or what is it going to experience? That's the first question. The reason why this question matters is that we were trying to highlight that you will have every possible orientation. So let's say that somehow you prepared the alpha state at a certain orientation with respect to the z-axis. Will its x, y projections change anymore? Does that make sense? It's an important question to ask, because what's happening here, if the spin orients itself at an angle with respect to B naught and it does not change, it yet again violates the quantum principle of uncertainty. The reason why I'm saying this is that at that point, if you drop this thing and then get the projection doesn't change. But in reality, the nuclear spin does not remain static with respect to the static magnetic field B naught. It experiences a motion which is referred to as precession. Please don't confuse with the word precision. Precision is has a different meaning. The motion precession means the angle theta with respect to B naught will remain constant, while about that axis, the spin will keep moving around in a cone. So basically what's going to happen, this is going to keep moving around over and over and over again with respect to the z-axis. That motion of a spin with respect to B naught is commonly referred to as precession. This motion about an axis is already defined as precession. Earth also has a precession axis, if you guys may realize, right? Earth's axis of rotation about its own self is not perpendicular to the motion that it has around sun. It's actually at an angle, right? The Earth rotates at an angle, and then the Earth also revolves around the sun, right? So that's a kind of motion that we are imagining. Please remember, there's no classical analog for this. But what we are trying to highlight to you is that if you take an isolated spin half, it also precesses about the B naught. Now, therefore, if you take an ensemble of spins, each spin precesses. And the precession frequency is what we would like to look at. And interestingly, the precession frequency is the same gamma h cross B naught. Okay. So for a given spin, for its gyromagnetic ratio suspended in a B naught, even the frequency of rotation, what's frequency of rotation? Number of cycles it completes per second. So you can imagine if you suspend a spin half system like a proton in 11.74 Tesla, about the B naught, it undergoes 500 million rotations about the B naught axis. Does that make sense? That's 500 megahertz. Okay, the energy difference also matches with the precession frequency. Therefore, if you have a bunch of spin half systems, let's say another one started off here, the relative phase between these two spins will be constant. They will never merge with each other because both are going around in the same frequency. Does that make sense? And therefore, what ends up happening, you have a cone that keeps also precessing about the B naught axis. The same thing happens for the beta state as well. Is everybody clear? If there is a question, please unmute and ask.
Yes. Sir. Would you explain how the precession frequency actually equals energy difference? I didn't really get that.
I'm not able to get your question completely. Precession frequency what?
You said the precession frequency is equal to the energy difference between
it happens
energy
to
gap,
be in such a
right?
case. It happens to be the case for NMR, and the precession frequency also goes with gamma h cross B naught.
Yeah, why would that be? Like, is there an explanation?
There is an explanation for it. I'll reserve that for later because I want to get the concepts clarified first and then move on to something else. Okay? Because if we go into, see, once again, I've had questions like what's a spin? Why should spin exist? If we go into some of these things, we will spend lectures after lectures and not getting into the depth of NMR that we want to go into. Okay, I'll try to give you an answer for it as soon as I can. Okay?
Sure, sir. Thank you.
Yeah, but it happens in such a way. This is also why The mere fact that the precession frequency matches with the energy difference is why NMR can actually be visualized even in a classical sense, although it's a quantum phenomenon, which is where we can actually show a classic magnetic field equivalent. That's why this treatment is called semi-classical, because unless you invoke the spin, you cannot understand how a bulk magnetization came up. But the moment the bulk magnetization has come up, you can actually treat everything classically, which you will see as we go forward in this class. That's why it's semi-classical treatment. You start with quantum treatment to talk about nuclear spins, and then get to bulk magnetization. The moment you get to bulk magnetization, you accept all information is in there, which we will discuss today. And then how do you extract that information out of it? Okay. But the most important thing that you must not forget is that there is a precession frequency where it is going to be given by the gyromagnetic ratio and the strength of the static magnetic field. And one important thing that I should make you guys observe here, since it's based on the gyromagnetic ratio, if you assume gamma greater than 0 has a clockwise precession, then gamma less than 0 will have a counterclockwise precession. So once again, I highlighted initially in one of the lectures where gyromagnetic ratio be positive or negative. In addition to the fact that if the gyromagnetic ratio is negative, the beta state will be the lower energy state and alpha state will be the higher energy state. In addition, one more thing happens. The thing is the sense of precession, the direction of precession of a nuclear spin with B0 will reverse as well. Now, if you ask me whether gamma greater than 0 is clockwise or counterclockwise, I don't know. Actually, I don't need to know at this point of time. If it's clockwise for gamma greater than 0, then it's counterclockwise for gamma less than 0. Okay. So this is also another effect that comes when precession, the gamma is less than 0. There's a small difference. Okay. But once again, whatever you learn for gamma greater than 0 can be flipped and you can understand gamma less than 0. So the treatment remains the same. Okay. Now that we have understood this, now how does this end up affecting the bulk magnetization M0? What do I mean by this is that we saw in the previous class, you have a bunch, you can think of it as a bouquet of nuclear spin vectors having a certain length and having its own precession frequency with a certain population difference at equilibrium, resulting in a net bulk magnetization, which is along B0. So now you have a magnetization parallel to the magnetic field. Do you realize now this bulk magnetization behaves like your classical magnet? It aligns itself parallel to the Earth's magnetic field at equilibrium. Make sense? Yeah?
Sir.
Yes. Go ahead, Deeptanu.
No, sir. There's no
Okay.
question.
Okay. I thought somebody said sir unmuted, so therefore I asked. You had a question. Okay. We will think about it. Am I making a mistake in the units? It's going to be gamma B0. Okay, in radians, that's right. No, that's correct. Yeah, that's correct. Okay, that's correct. There will be no H cross there, largely because, correct, I should have been careful. So it's H bar omega naught, right? And if you want the angular frequency, the H bar should not be there. You're correct. Thank you so much. It's gamma B0, it's not gamma H cross B0. Otherwise, the units don't match, right? Okay, done. So now, the interesting aspect of this is that you created a bulk magnetization that is parallel to the static magnetic field. Interestingly, for angular momentum, the rate of change of angular momentum, which is given by dj over dt, is given by m cross b. It's a cross product of the magnetization to a field that is applied. These are physics principles. Is that right? The rate of change of angular momentum is given by the cross product between the magnetization and the magnetic field, where the cross product is mod m, mod b, sine theta, n cap, where n cap is perpendicular to the plane containing m and b, and theta is the angle between the vectors m and b. Correct? Therefore, if you're trying to ask what will be the change of angular momentum for the magnetization, bulk magnetization that's created at thermal equilibrium, you would want to apply this expression. And what are you going to get? You see that M naught and B naught are parallel to each other. Since there is a sine theta dependence with theta being 0, you realize that there is no net change of angular momentum for bulk magnetization. Okay? This is important to understand because if you want to extract information from this bulk magnetization, how will you do it? Of course, you can do something called magnetometry, where you measure the strength of this bulk magnetization. But for all all practical reasons for this course, we will not be worrying ourselves about magnetometry. We are going to be worrying about magnetic resonance, meaning that how are you going to disturb this magnetization to make a measurement? Why do you have to disturb this magnetization? You realize that the magnetization and the magnetic field are collinear. If they are collinear, there's no rate of change of angular momentum. Why do you need a rate of change of angular momentum? If the magnetization doesn't move, how are you going to measure it? Why do you need a magnetization that moves? Because magnetization that cuts a current coiling conductor, the coil that can take current, then you induce current in it. These are very basic Maxwell's rules, right? So where you have a magnetization that cuts a coil, then it induces a current in it. Does that make sense? But in its current form, which is a bulk magnetization that is parallel to the static magnetic field, there's no change of angular momentum. Therefore, that's going to remain also static. So what do you have to do? You got to disturb, or in more technical terms, perturb the equilibrium magnetization, M naught. Because unless you disturb it, you're not going to make a measurement. And right now, let's not worry about how we make this disturbance. Assume that you have all the powers in terms of the RF field that you apply, where you apply light and you do spectroscopy, isn't it? Where the RF field that you apply can change this magnetization. And how does that happen? You can always apply a magnetic field. Remember, you can only affect a change when the M and B are not collinear with each other. So in addition to this B naught, you have to apply another BRF, which is your equivalent of a light that is perpendicular to M naught so as to cause a disturbance. Because that's when the M cross B is non-zero. That's when you can affect a change with respect to M naught. And yet again, the motion that the magnetization occurs, the motion that the magnetization experiences with the effective magnetic field is also precession. Okay, meaning that we do some magic, which I can't go into details in today's class. We'll do tomorrow's class, and that also gives me an avenue to say Friday morning we have a class. So please be here. Saturday also we'll have a class this week to make up for last week's class. Okay. For now, I cannot say how B naught vanishes suddenly. Assume that we have all powers within us where we apply a magnetic field, effective magnetic field that's perpendicular to M naught with no B naught being present. And therefore, what is going to happen? M naught is going to precess about the effective B that you have applied. And therefore, you can move the M naught wherever you want. So let's say that we started with this kind of a case. Where you had the M naught collinear with B naught, then you applied an RF pulse. There's something called on resonance RF pulse. Once again, don't worry about these terms. We'll go look at it later. And what do we mean by this is that you apply the RF pulse, let's say along the x-axis. You have a precession motion of M naught with respect to this effective B right now. Why is it applied perpendicular to M naught? Because once again, the cross product will be maximum when you end up doing this. And therefore, what happens now, for some reason, the B naught is not present and you only have the effective BRF. And therefore, the M naught is going to precess. If you apply the RF pulse along the x-axis, the M naught will precess about the YZ plane. It will keep moving until you keep applying the RF pulse. So you have the power to apply the RF pulse to get the M naught wherever you want it. And for sake of discussion yet again, let us say that we applied for a certain duration such that your M naught is perpendicular to from wherever it started. How do we do this? We are applying a pulse along the x-axis. Let's say the M naught precesses, but somehow when it comes to y-axis, we turn it off. Okay, that's what is the pulse. Therefore, you apply the pulse for a short duration. That's also why it's referred to a pulse. You don't apply it forever. It's a very short duration perturbation, which is what we refer to as a pulse. Now remember, the moment you turn off this RF field, what is going to happen? The influence of B naught is going to come back up, meaning that whatever was invisible is going to come back up. Let's go back to the angular momentum expression. Previously, you couldn't measure the magnetization because the M and the B were collinear. Now, by the use of the disturbance, what you have done effectively is to get the bulk magnetization along the transverse plane. For sake of argument here, along the y-axis. Now, B naught is still present. Now, what happens to M naught? M naught starts to precess about B naught in the xy plane. Now, let's say you are able to keep a coil somewhere here. Then what is going to happen? This magnetization that keeps cutting a coil will induce a current, and you can make a measurement of this current as a function of time. Coil and measure current as a function of time. And remember, this magnetization that cuts the coil induces a current. So, which is also why it's called magnetic induction. The magnetization cuts the coil, therefore induces a current. That current magnitude you will be able to measure, okay, as a function of time. Yet again, what is going to be the frequency of this measurement? Let's try to plot it. Let's say you're going to measure current as a function of time. And just for the sake of simplicity, shall we move this coil to the y-axis? Say I move this coil to the y-axis. Okay. What is going to happen? At zero time, meaning after the perturbation, or the moment I stop the perturbation, I make a measurement, I get the maximum current. And the maximum current will be proportional to M naught, meaning the length of the vector. But is the vector going to be static at that point? Remember, B naught came back up. Therefore, the M naught is going to be precessing about the B naught. Correct? And this precession frequency is once again going to be the Larmor precession frequency. I don't know whether I wrote the name. Larmor precession frequency. And what is that going to be? In this case, if you have it's going to be gamma B naught. And therefore, what are you going to end up measuring here? You're going to end up measuring change of this magnetization over a period of time. So let's assume that it has a clockwise precession with respect to z-axis. So it's going to start off along the y-axis, the way we have shown it, and it's going to keep on moving around. And your coil is static, meaning that if you want to measure the current, what is going to happen? This vector keeps on moving away. And at some point, it's perpendicular to this. Will it measure any current? No, it will not. As it keeps on going here, it will measure no current. At this point of time, it will measure an opposite current of an opposite magnitude. Then it comes back up and maximum current. It keeps on doing this over and over and over again. So what is going to happen? You're going to end up having a sinusoidal distribution. where this is one period of one full cycle and it keeps on going. And the frequency here is going to match the Larmor precession frequency. So far, so good. If people have questions, please unmute and ask questions. So therefore, as a function of time, if you measure this signal, you'd be able to pick up a frequency. And if you're confused what molecule you have to imagine at this point of time, you can, for the sake of simplicity, imagine water molecule. Take a test tube of water. It has two equivalent protons. Each of the proton is either going to be an alpha state or beta state. Given it's an ensemble average, you're going to generate an M naught parallel to B naught. And now we have applied an RF pulse such that you get it at the transverse plane, and it's going to, the signal is going to go on forever, although not true for the first case scenario. And therefore, what is going to happen? You're going to measure this frequency. You're going to measure in the time period, but from time period, can we get frequency? Yes, you can, right? These are inversely proportional to each other. Therefore, you'd be able to get the frequency. The moment you get the frequency, you know what is the Larmor precession frequency. We'll take an example of methanol before the end of the class so that you understand how do you get separate resonances of the methyl and the hydroxyl. But for now, you just have water molecule, you get the Larmor precession frequency. Make sense? Now, the important aspect that we have to go back and understand a little bit further is that you have generated something called a non-equilibrium condition. If you let things be, the classical magnet likes itself to be parallel to the B naught. But you've now created a condition where the magnetization is not parallel to the B naught and it's actually perpendicular. And if you're thinking about it, you're going to have minus mu dot B naught, minus mu dot B, right? And the dot product, and therefore it's going to have a middle energy. It's not going to be of the energy that you started off with, right? So basically it's of higher energy. The system has been prepared in a higher energy state, which is not an equilibrium state. It's a non-equilibrium state. So therefore what happens? Slowly the length of the vector becomes smaller and smaller. We'll understand the mechanism of why the length of the vector becomes smaller and smaller. And therefore what is going to happen? Although you might have expected to measure frequency that keeps on oscillating over and over again, in reality, the frequency remains same, but the intensity gets dampened as a function of time. This is a very realizable reason why this happens. Let me try to draw it as properly as I can. So, dampened oscillations. Why do the dampened oscillations happen? Because you created a non-equilibrium state. Any non-equilibrium state tries to go back to equilibrium. What is equilibrium? No magnetization along the transverse plane. And therefore, slowly it will go and then go to nothing. How does this dampening happen? We'll look at it in the nuclear spin perspective in a moment. I hope you guys have understood that you have a bulk magnetization that you cannot measure that easily unless you do magnetometry, but we are doing magnetic resonance. In order to measure it, you want to have the magnetization and the effective field not being parallel. So you apply a RF field to get it to the transverse plane, turn off the RF field, let it precess, keep a coil, it induces a current, and you measure the current as a function of time, which slowly decays. Okay? This signal is referred to as free induction decay. This is a very important term to understand. What is free about it? What is free about it? The mere fact that once you've created a non-equilibrium condition, the magnetization freely precesses about the B naught. And the freely precessing magnetization induces a current in a coil which you can measure. And this current decays over a function of time. Because you create a non-equilibrium condition, it tries to go back to equilibrium. The process of moving from non-equilibrium condition to equilibrium condition is called relaxation. If you want an analog for what you're trying to think, I'm sure this NMR course is a non-equilibrium condition for many of you. It's making you think your brain is working too hard. And if you let your brain be happy in thermal equilibrium, you don't want to think, correct? So over a period of time, you reduce your thoughts after this class or realign to something else. So that's a relaxation process. So that's what we do, right? On a weekend, when we don't want to think about something, that helps you come back and perform better. Because you cannot keep working all the time. So relaxation is an important aspect, not just for you and me, but also for nuclear spins. The mere fact that you started in a non-equilibrium condition and let this happen over a function of time, this signal decays, and it's often the signal that we measure after the perturbation is often referred to FID, free induction decay. But we wanted a frequency, we are getting a time domain signal. So you take the free induction decay and put it through something called a Fourier transformation. You will end up getting the frequency domain spectrum. As chemists, we like to look at chemical shifts, which are all in frequencies, at least relative frequencies. And therefore, you started with a time domain signal. If you're asking for the direct correspondence, let's say the time domain signal is given as a function s of t. And the frequency domain spectrum is given as capital S of omega. You would end up getting the capital S of omega by doing a Fourier transformation of practically from minus infinity to plus infinity. But here we'll restrict it 0 to t because after the perturbation we define 0 time, or rather when we stop the perturbation we define as time 0, and we go until a certain amount of time until the signal has completely decayed. And then you have S of t e power minus I omega t dt, meaning that you have a time domain signal with an integrand, which is a Fourier integrand. If you integrate it over all time, it should be minus infinity to plus infinity, but you have no signal from minus infinity to 0. And then from 0 to infinity, you'll have signal. But after a point, since due to decay, there'll be no signal after a certain duration. So you cut the measurement after a certain time t. If you do a Fourier transformation, you'll be able to get a frequency domain spectrum. Meaning, whatever you started off with, if you had S of t as an oscillation, when you end up Fourier transforming, you will be able to get a frequency domain spectrum. Okay?
Sir,
Yes.
in the time domain signal, the signal we are considering is the current.
Signal is measured in the form of current, correct? Yeah.
How is the current decreasing with
The magnitude of the vector becomes smaller and smaller over a period of time. Remember, your thermal equilibrium condition is no magnetization along the transverse plane. Therefore, you're in non-equilibrium condition, it goes towards equilibrium. Therefore, the length of the vector becomes smaller and smaller.
is it because it's going
Why is it because? We'll come to in a moment. Let's not go there. I've not explained that yet. Okay. So far the signal is clear. How do we get the spectrum from the signal is a little clear? Okay. Now we'll get into the understanding of, first of all, how are we creating a state without understanding the quantum mechanical underpinnings? Why does this matter? Because we said that quantum magnets do not behave as classical magnets, meaning that every possible orientation is not feasible. Therefore, you're somehow creating this entire system with the quantum spins in a very interesting manner. And how are we doing it? So this requires once again your attention. Instead of writing the notes, please pay attention to the board. So maybe I can draw it again. This was the equilibrium condition. Interestingly, what happens when you end up applying an RF pulse? I'm going to introduce terms slowly. What do I mean by this? It's actually a minus X phase pulse, but we'll leave it here. So let's say you're applying the 90-degree pulse along the X phase. The magnetization finally comes under the Y-axis, bulk magnetization. But you cannot change the eigenstates of the nuclear spins just because you applied an RF pulse. So how did you suddenly create a transverse magnetization? That needs explanation, right? So what does the RF pulse do? The RF pulse works on every spin that is being present, pushing it towards one part of the cone. The RF pulse does work in order to minimize the phase decoherence between the spins, meaning that in the initial state, each of the spin are not coherent. What is coherent? Together, are not bunched up. They're random. But on the other hand, when you're applying the RF pulse, you can imagine it does individual job by moving each one of them to one part of it. So therefore, what effectively happens is all the spins get bunched up. You remember I was telling you, given the uncertainty that exists, you cannot have them in the same place when you prepare the system. But if you do work, you can always bunch it up. Recollect the laws of thermodynamics. The total entropy of the universe keeps increasing. But there are enough examples in our life where when we do the work, the entropy of the system reduces. The classic example of this is how you make ice in your freezer. The entropy change of water to ice is negative, meaning that water is more ordered in ice than water, the state of water, liquid state. But how does that happen? How does reduction in entropy come for the system? It comes at the expense of the refrigerator outside being hot. So the amount of entropy that increases in the surrounding is much more than the entropy decrease in the system. Therefore, you can, similar is what the pulse does here. The pulse reduces the entropy of the random spins being there and does work to go to an ordered state. And the ordered state is when all the spins are bunched up together. And this state is called the coherence. And what coherence? It's called phase coherence. You may remember I started off the class by trying to say if there are two of them, since their Lama precession frequency is same, their relative orientation remains same. So basically they have a phase difference with respect to each other. Okay. So therefore they are phase decohered in the equilibrium condition. On the other hand, after you end up applying a pulse, the phase bunching happens, which is called phase coherence is generated for the alpha state and the beta state. For a 90-degree pulse, one more thing happens, which you will learn later on, where initially you started with P alpha and P beta being different. The moment you ended up applying the 90-degree pulse, the populations become equal on both the alpha state and beta state, in addition to having their phase coherence. So the RF pulse achieves two things: population equalization across alpha beta states and introducing a phase coherence between the alpha spins and the beta spins. Okay, and since these are both are together, you get a net magnetization that now points towards the y-axis. Yet again, if you take these two vectors, the resultant of those two vectors will be perpendicular, or rather, the resultant of the alpha state bunched vectors and beta state bunched vectors will be in between these two, and that's the bulk magnetization you're measuring. And what I would therefore like to remind you again is in the equilibrium state, M naught arises from phase decoherence in the transverse plane and population difference between the alpha and beta states. On the other hand, after the 90-degree pulse, the non-equilibrium state, which also in this case has the magnitude of m naught, is created with phase coherence and no population difference. Now, if we ask ourselves, the answer will be straightforward: why the length of the magnetization m naught decreases as a function of time. Remember, you have created a non-equilibrium state, not just in terms of population, but also in terms of phase coherence. These guys are not happy being wherever they are because energy was supplied to make them bunch up together. The energy that I am putting here is helping you understand NMR better. So that's the phase coherence that's being generated and the effort is coming from me. Right? But the moment I leave the class, you guys are probably not going to be thinking about NMR and start thinking about other things, which results in this phase coherence starting to lose itself as a function of time to go back to the equilibrium state, which is no phase coherence, random phase along the transverse plane. And therefore, when that happens, you can imagine the bunched up vectors slowly start becoming less and less bunched, and then will be equally distributed around the cone, which is what is the equilibrium state. And therefore, what's going to happen, the length of the vectors is going to keep on reducing, the length of the vectors along alpha and beta states start reducing, the length of the m naught reduces, and therefore there's a decay in magnetization. Yet again, the move away from non-equilibrium state towards the equilibrium state. Okay. Simultaneously, another thing also happens. What is the another thing? We said the population, unequal populations become equal after the 90-degree pulse. That also reverses back. This is important to note because the bulk magnetization came due to population difference. The moment you applied a 90-degree pulse, the population difference vanished, and therefore there is no magnetization along z-axis. There is only magnetization in the xy plane. The moment you turned off the RF pulse, the phase decoherence happens, length of the vector reduces, this transverse magnetization decays over a function of time, while the longitudinal magnetization recovers over a period of time. Because that's also in a non-equilibrium state. Z magnetization, the equilibrium state had m naught. After the 90-degree pulse, you took it to 0. So the recovery back from 0 to m naught also happens along the z-axis. So in order to understand this, we tend to refer these two to a certain recovery of longitudinal magnetization. Is referred to as spin lattice relaxation. What is spin and lattice here? You created a bunch of spins that are coherent, or in this case, the populations have become equal. And the lattice is the surrounding system which ends up exchanging energy with it so as to restore back the equilibrium. Since these were all thought about in solid state matters, the spin and lattice word came up. Is also referred to as longitudinal relaxation. And remember, longitudinal magnetization is dependent upon population difference. And now, loss of transverse magnetization. What do we define as transverse? Anything that's perpendicular to B naught. The xy plane is what we refer to as the transverse plane. Transverse magnetization is referred to as spin relaxation, also known as transverse relaxation. Remind yourself that the transverse magnetization is a result of phase coherence. So the process of phase decoherence is transverse relaxation. Since you realize these two magnetizations, although have the same magnitude m naught, but the reason why they come up are different, their kinetics are also quite different from one another. Where the transverse relaxation time is referred to as T2, while the longitudinal relaxation time is referred to as T1. And generally, T1 relaxation times are longer or equal to T2. This is very important to note. Why is this important to note? Meaning that the signal dies faster than recovery to its equilibrium. You will understand the implication of it as we go further, meaning that we said NMR is an intrinsically insensitive spectroscopy. Therefore, you have to repeat the same experiment multiple times. At that point, this point will come back where you cannot repeat the experiment without stop. It's like literally having 10 NMR classes back to back to each other right now. Will you guys be able to understand anything? You'll be saturated after maybe 2 minutes now. And then if I keep repeating whatever amount of topic I give, you would probably not assimilate it. Same way the nuclear spins also behave. Meaning that you excited it, you measured the signal. After the signal has died down in the transverse plane, you still have to wait a little longer for the longitudinal recovery to happen so that you can repeat the experiment and go on in multiple cycles until you get the desired amount of signal to noise ratio. It's very important for you guys to, first of all, note that the transverse and longitudinal relaxation mechanisms are different. And generally, the longitudinal relaxation time is much longer than the transverse relaxation time. Just to give an idea, for proteins, the transverse relaxation time will be in the period of 100 milliseconds, while the T1 will be of say 1 to 2 seconds. So although you may think that 1 to 2 seconds is short, you will realize you have to repeat the experiment multiple times. Here I have to highlight for small molecules, like the molecules that chemists end up preparing, the T1 times will be in the order of say 2 to 3 seconds, and the T2 times will be in the order of say 0.5 to 1.5 seconds. They are generally longer. As the molecular size becomes bigger and bigger, T2 times gets shorter and shorter. This is important because therefore your amount of measurement time reduces. Yet again, going back to Heisenberg's uncertainty principle, if you're not able to measure long in time, your frequency uncertainty increases a lot. Think about position and momentum. If you're able to get position properly, momentum cannot be measured. Similarly, if the amount of time you're able to measure the transverse magnetization is low, then the uncertainty in frequency domain is high. Therefore, the line widths will be higher, which I would have referred to in passing in the earlier classes, where I would have said the line width also has some information embedded in it. Okay, the lines will get broader and broader. As the lines get broader and broader, the intensity becomes lesser and lesser because the area under the curve has to be maintained. And there will be a point where the line is so broad, it will be within the noise level, you cannot see it. So as you go larger and larger in size systems, solution state NMR suffers in having broader and broader lines. Okay, so with this, any quick questions from any of you guys? Please unmute and ask. All we did today was to understand and appreciate how does a bulk magnetization, if perturbed, can help you record a signal, and how the recorded time domain signal gets converted to frequency domain. And how do the signal ends up decaying as a function of time? Why does it decay? First of all, how was the transverse magnetization generated? After you apply the RF pulse, you create ordering of the spin phase coherence, and you create a transverse magnetization, therefore, which when you turn off the RF, cuts the coil, you pick up the time domain signal, Fourier transform it, get the frequency domain spectrum. Yes, Deeptanu.
So why is the recovery of longitudinal magnetization called the spin lattice relaxation?
Spin lattice relaxation is the recovery of longitudinal magnetization back to equilibrium, where the population comes back from a non-equilibrium state. If you may realize, the populations became equal, therefore there's no Z magnetization. Therefore, the recovery of P alpha greater than P beta from P alpha equal to P beta is the spin lattice relaxation, which is longitudinal relaxation.
Lattice here refers to the environment, right?
Yes, it refers to the surroundings of the spin. Correct.
Yeah.
The word lattice may be confusing, but that's legacy word that comes from initial physics theory, where they were treating the system as spin and the surroundings as lattice. That okay, Deeptanu?
Yes, sir.
Any other questions from others? Okay, if not, we meet 9 a.m. tomorrow to see this further. Thank you so much.